to spend today's lesson telling you about a useful, but ultimately incomplete, model for thinking about bonding, called valence bond theory. Like Fleetwood Mac, I'll tell you lies, sweet little lies. Valence bond theory approximates the bond angles that we saw in our molecular geometries in the last chapter, and we explained in the last chapter with valence shell electron pair repulsion theory, or VSEPR theory. Valence bond theory makes a lot of geometric predictions about molecules fairly straightforward, but it isn't a good description of what actually happens in a molecule's bonding, and it falls short when you try to describe things like magnetic character. Here we see in the picture oxygen's magnetic character as a liquid oxygen is caught between a strong magnet. And it also falls short when we try to describe a molecule's aromaticity. So why do we use it? Again, it makes straightforward predictions of molecular geometry that are reasonably accurate most of the time, and it's a lot easier to do on the fly. However, in the next lesson, we'll discuss molecular orbital theory, MO theory for short, a much more robust and complete treatment of molecular bonding. We'll see that MO theory is a bit more difficult to apply, especially to molecules with more than just a few atoms. For this reason, we'll continue to use valence bond theory throughout your chemistry coursework. It's easier for most things, but we'll also use molecular orbital theory descriptively for a lot of concepts. It's important for us to have a good foundation in each of these theories. Again, the picture shown on this page shows liquid oxygen being trapped by a magnet, an observation that's only explained by molecular orbital theory, as many complex properties of molecules are only explained by MO theory. Both valence bond theory and molecular orbital theory start out with a basic understanding that electrons in atomic orbitals have both particle and wave properties. Since our electrons are waves, they can overlap constructively and destructively. The more waves overlap in the same phase, the more they interact constructively, a bond. On the left, constructive interference leads to a bigger wave, indicating a bond. On the right, destructive interference leads to the destruction of both waves, the opposite of a bond, which we call an antibond. Starting with our atomic orbitals, it's easy to see that some arrangements will lead to better overlap than others, and therefore much better bonding. On the left, you can see two p orbitals centered around the nuclei of atoms represented by black dots, which are interacting head-on, which can lead to decent orbital overlap and a more stable bond. On the right, the orbitals are interacting at an angle, which doesn't allow for the same overlap and minimizes the stability of any possible bond. In both cases, the overlap is constructive. Colors are used in these diagrams to indicate the same phase. There are many ways that we can get this relatively direct overlap, which we call a sigma overlap, to form what we call a sigma bond. In fact, this is the only type of overlap possible for s orbitals, which is convenient because sigma is the Greek letter s. From left to right, these overlaps form most commonly from s orbitals interacting with each other, seen in A, or s and p orbitals interacting, seen in B, or p orbitals interacting head-on, which we can see in C. Notice that we flipped the rightmost p orbital 90 degrees in either B or in C. We'd end up with constructive interferences on one side, but the same amount of destructive interference on the other side. This means that the orientation of the orbitals for these overlaps really matters. Another way to think of sigma overlaps is that they will always look the same if you take a two-dimensional slice perpendicular to the bond, called a cross-section. The cross-sections of sigma overlaps are always circles. Once we have p orbitals, we can still have sigma overlaps if they interact head-on, as we just saw. But we can also get decent overlap if the p orbitals line parallel to each other, especially if the atoms are close together. It isn't as good as a sigma bond, but it's still stabilizing. This gives us what we call a pi overlap to form what we call a pi bond. The cross-section of pi orbitals has two distinct sections of overlap, or of opposite phase. Notice that the pi overlap, using the Greek letter for p, looks a little bit like a p orbital. P orbitals can form pi bonds with other p orbitals, but they can also form pi bonds with d orbitals of later elements if they overlap correctly. If we rotate one atom around the bond axis with a pi bond, the p orbitals won't overlap anymore, which is different than what we saw with sigma bonds, which can rotate freely along the bond axis. It's not like they're destructively interfering, it's not a sad face. The p orbitals just don't interact at all if they're rotated. Whenever we look at a Lewis structure, we consider the first bond to form between atoms a sigma bond. Sigma bonds give the most overlap, the most constructive interference, and therefore are the most stable. But no more than 2 electrons can occupy the same space, so we can't have another bond with the sigma overlap. Instead, additional bonds need to be using pi overlap, usually from p orbitals. So a molecule with a double bond has 1 sigma bond and 1 pi bond. A molecule with a triple bond has 1 sigma bond and 2 pi bonds. Here's a picture of ethene, CH2CH2, along with pictures that show its bonding orbitals. Each of the hydrogens is attached to a carbon by a sigma bond, which makes sense since hydrogen only has electrons in a 1s orbital. It could really only form sigma bonds. The carbons are also attached by a sigma bond with circular overlap. 2 electrons sit in each of those bonds. The double bond can sit both above and below the sigma bond without interfering with the bonding electrons, so it doesn't take up the same space. That would be a pi bond. Here's a picture of ethyne, CH-CH, along with pictures that show its bonding orbitals. Each of the hydrogens is again attached to a carbon by a sigma bond. The carbons are again also attached by a sigma bond with circular overlap. 2 electrons sit in each of those bonds. The double or second bond can sit both above and below the sigma bond without interfering with the bonding electrons, just as we saw before. The triple or third bond sits at a right angle to the other pi bond because it uses a different set of p orbitals and gives the same type of overlap. So every bond consists of a sigma bond, but double and triple bonds also have 1 or 2 pi bonds, respectively, as well. With this in mind, try to identify the number of sigma bonds in the structure shown, which is butadiene. Then try to identify the number of pi bonds. Here are the sigmas, 1 between every set of bonded atoms for a total of 9 sigma bonds. And the pi bonds are only in the locations where there is a double or triple bond, so only 2 pi bonds. Up until this slide, everything that we've done actually applies to both valence bond theory and molecular orbital theory. As soon as we quantified the number of sigma and pi bonds based only on the valence electrons shown in the picture, we put ourselves squarely in valence bond territory. That's okay. I just wanted to name this as the first point of divergence. We run into an interesting problem with our overlap theory of bonding. The overlap makes sense, but it does not at all explain the geometries that we actually see. This is a picture of how 2p orbitals from oxygen could overlap with the 1s orbitals from hydrogen to make water. We know that we can't be strictly using p orbitals. They exist at right angles, 90 degrees from each other. Yet we find that water's bond angles are 104.5 degrees. Valence bond theory and molecular orbital theory both address this in different ways. Valence bond theory recognizes that VSEPR theory, that's the valence shell electron pair repulsion theory, actually gives us bond angles that are really close to this and seeks to explain how we can get there from linear combinations of the atomic orbitals that we know exist. So essentially saying, how can we add the orbitals that we know exist together to make this work? A linear combination is when you add or subtract 2 orbitals to make a new set of orbitals. In a linear combination, the number of orbitals you are combining will always be the same as the number of resulting combination orbitals. So if we take 2 and put them in, we end up with 2 resultant orbitals. Those combination orbitals are called hybrid orbitals. They are a trademark of valence bond theory that causes molecular orbital purists to cringe, but they are really helpful bridges between atomic orbitals and the types of molecular geometry observations that they explain well. The simplest linear combination is from taking an s and p orbital in the valence shell and adding them together. We can see the s and p orbital in blue and red and blue on the left. Since the p orbital could be in either phase, having the red and blue as shown or flipped, it adds in 2 different ways. The hybrid orbital on the left comes from adding the s and p orbitals exactly as shown. The blue regions overlap constructively and add together, so the right becomes bigger, and the red and blue interact destructively, so the left gets smaller. The hybrid orbital on the right comes from the p orbital adding when it's in the opposite phase, the red on the right and the blue on the left. In this case, the constructive interference is on the other side. The orbital looks identical, but is flipped 180 degrees. Whenever one of these orbitals occurs, the other also does, and if they always are going to be arranged 180 degrees from each other. If they're used for bonding, the atoms will be attached 180 degrees from each other as well. Because this simplest linear combination uses just one s and one p orbital, we call each of the hybrid orbitals sp orbitals, and we say that the atom has sp hybridization. When we combine orbitals, we don't just combine their shapes, we also combine their energies. So if we take a beryllium, which normally has 2 electrons in the 2s shell, and hybridize it, that hybridized orbital mixes one of the p orbitals with the s orbital to give 2 orbitals that are in between the s and p orbital energies, and degenerate, meaning they have the same energy. This looks like it wouldn't be favorable. The electrons increase in energy in this case, but they would actually decrease in energy when they bond. sp hybridization tends to occur in triple bonds, which use 2 unhybridized p orbitals to form pi bonds, in addition to using the sp orbitals to form sigma bonds. It's a little bit harder to see how linear combinations work in 2 dimensions, but when we combine an s and 2 p valence orbitals, we get similar shaped orbitals that are held a little farther from the nucleus and have a little higher energy. Because the p orbitals that are contributing to the hybrid orbital are in 2 different axes, as shown in the px and py orbitals, the resulting orbitals sit in the xy plane, evenly distributed. Since we are combining a total of 3 orbitals, we end up with 3 hybrid orbitals distributed evenly without that plane, shown in the top right in yellow. They're all degenerate, meaning they all have the same energy. The 3 atoms that could be bound to our central atom with this sp2 hybridization from 1s and 2p orbitals would be spaced 120 degrees from each other, evenly spaced in 2 dimensions, which matches with Vesper theory trigonal planar arrangements. Again, this changes not just geometry. If that was the case, we could just keep on using valence shell electron pair repulsion theory until we ran out of breath. This also means that the hybrid orbitals will have new energies. In BH3, a molecule that doesn't truly exist freely in this form, the 2s orbital of boron combines with the 2 of the p orbitals to make 3 degenerate orbitals, about 2/3 of the way up from an s energy to the p energy, and leaves 1 p orbital unhybridized at a higher energy. Again, even though it looks like we're in a higher energy conformation, each of the hybrid orbitals can now interact with hydrogen to drastically decrease their overall energy. The leftover unhybridized p orbital is able to form a pi bond. In most cases, sp2 hybridization occurs when the atom is double bonded. Notice that every double bonded atom has 3 groups of electrons, which would give us trigonal planar configurations in Vesper theory. Trigonal planar is analogous to sp2 hybridization, so if you can recognize when an atom should have trigonal planar arrangements, you can also recognize its hybridization as sp2 hybridization. We can also linearly combine all of the p orbitals with the s orbital to give sp3 hybridized orbitals. These orbitals will then look the most like p orbitals and have their electrons held at higher energy and farther out, because they're 3/4 p orbitals and only 1/4 s orbital. Since p orbitals are used in all 3 dimensions, the resulting shape is a tetrahedron, which can also only be described in 3 dimensions. So tetrahedral and sp3 go together just like trigonal planar and sp2 go together, and linear and sp go together. sp3 hybridization combines all the valence orbitals and gives hybrid orbitals that are again each 25% s and 75% p. So they have energy that's about 75% of the way up to the p orbital's energy, and they're all degenerate. Since all of these hybridized orbitals have one large lobe on one side and one severely diminished lobe on the other side, they are suited well to interact with other similarly hybridized orbitals, or with hydrogen to give sigma overlap and form sigma bonds. We know from our discussion of valence shell electron pair repulsion that some transition metals and 3rd or greater row nonmetals can adopt more complex geometries, like trigonal bipyramidal geometries or octahedral geometries. In these cases, d orbitals also have participated in the linear combination. A trigonal bipyramidal configuration corresponds to an sp3d hybridization and gives 5 degenerate orbitals, as shown. Remember that we're always talking about all of the electrons for the overall geometry that matches with hybridization. These three molecules are all sp3d hybridized, but the atoms alone give shapes that are known from left to right as seesaw, T-shaped, and seesaw again. But it's the electron configurations that matter. Octahedral conformations correspond to sp3d2 arrangements with 6 degenerate orbitals. The other geometries that have octahedral overall configurations but have one or more lone pairs still will have the same sp3d2 hybridization. Even though hybridization makes sense of the geometries we see in the earliest parts of the periodic table, we see that as we move farther down the periodic table, here moving from H2O to H2S to H2SE, down the chalcogons, oxygen, and below from left to right, the geometries look more and more like they occur from unhybridized p orbitals. We've hinted a little that our unhybridized p orbitals will be able to react. Here's an example where that's fairly straightforward. Ethene, CH2CH2 or C2H4. When carbon hybridizes to sp2, its 4 electrons can each be distributed to a different set of orbitals. 3 electrons to sp2 orbitals that will be used to form sigma bonds, and the 4th is left over in a p orbital. That electron in a p orbital can interact with another electron in a p orbital to form a pi bond. So using our double bond from before, each carbon will have 3 sigma bonds using sp2 hybridized orbitals. But each carbon will also have a pi bond with the other carbon using an unhybridized p orbital. So how do we get a triple bond or 2 pi bonds? We just need to have sp hybridization that leaves 2 p orbitals that are on the central atom. Each of the p orbitals can interact with a parallel p orbital to form its 2 sets of pi bonds. This is commonly a triple bond, but it can also actually be double bonds that are on either side of the same atom, like in carbon dioxide. Here's an example of how that looks in ethine. The sp hybridized orbitals are 180 degrees from each other, which is why the entire molecule is arranged in a straight line. You have those hydrogens binding on and making sigma bonds, and of course you have a sigma bond between the carbons. But you also have a pi bond in the vertical plane and a pi bond in and out of the plane to make a total of a triple bond between those carbons. Because more than one set of p orbitals can align parallel to each other, they can actually combine across many atoms to make delocalized pi bonds spread across every participating atom. In the benzene molecule shown, our simple descriptions of either a single bond or a double bond belie the experimental observations that every one of those bonds is identical to each other. Valence bond theory does a poor job with delocalized bonds, one of many reasons that it's important for us to understand molecular orbital theory, even if we continue to use valence bond theory and hybridized orbitals in many of our simpler examples.